All right, welcome back to Math 160. So last class we finished section 6.2. We actually had one question that I wanted you to take home. So I'm just going to show that to you briefly. That was on page 15, problem number 9. We were given the mean and the standard deviation, and we wanted to find the salary that separates the bottom 2.5% and the salary that separates the top 2.5%. What we want to start with is the lower end here, since we know that the z-score table provides the areas to the left of a z-score. So essentially, we know that the area to the left of this particular z-score is 0.025. When we went to the chart itself, the z-score table, we found the area inside the chart. So let me just show this to you really quickly. We were looking for 0.025 as our value. When we look for 0.025, notice that here's my area, and that pertains to a z-score of negative 1.96. So once I found my left-hand z-score, negative 1.96, I also found its opposite, which is a positive 1.96. You use those values in your z-score formula, where it's z is equal to x minus the mean divided by standard deviation. We go ahead and we solve and we find the salaries that separate the bottom and the top. So notice the content that I have here and the description as well. Hopefully you had the exact same answer as you worked through this on your own. Notice the note at the very bottom, do not confuse z-scores and areas. Remember that z-scores are distances along the horizontal scale. These are z-scores here. But areas are regions under the curve. So for instance, if I were to shade this region, that has an area of 0.025. The region above also has an area of 0.025. Okay, so be really careful discerning between those two. Next, we're moving into 6.3, sampling distributions and estimators. So in this section, we consider the concept of a sampling distribution of a statistic. So we're going to be focusing on samples obtained from the same population. So think about just taking more than one sample from the same population so you can do some comparison. Definitions. The sampling distribution of a sample statistic is the distribution of values for any sample statistic obtained from all possible samples. So essentially, this is through repeated sampling and all of the same size and all drawn from the same population. All right. So if your first sample, for instance, had a size of 10 individuals, and your next sample also has to have 10 individuals, and the sample after that, and the sample after that, et cetera, et cetera. So you want to make sure that they're all the same sample size from the same population so that you can do some comparisons. Next, the sampling distribution of the sample mean. Notice the sampling distribution of the sample mean. That's actually abbreviated SDSM, the sampling distribution of the sample mean, is the distribution of all possible sample means with all samples having the same sample size n taken from the same population. I have a nice visual here that kind of shows exactly that. Notice the sampling procedure, it's randomly select n values and find the mean. The population mean is mu, so notice the difference. The sample mean is x bar, population mean is mu. Each sample has its own mean, so we're essentially looking at the distribution of those means, okay? We're looking at the distribution of all of those means. The diagram above shows a distribution of sample means. So for example, there are 50 different researchers collecting a random sample of 50 people from the same population. Each researcher calculates the sample mean for their sample. Notice the sampling distribution of sample means is a normal distribution. So it's approximately normal. All right. And we can see that in the diagram, which is actually a pretty cool feature. Let's turn the page. Constructing a sampling distribution of the sample mean. So we're going to learn how to actually build a table with this given information. Let's consider a very small finite population of values. Let's say the only values you have are 1, 3, and 5. We want to construct the sampling distribution of sample means for all samples of size 2, right? That means n is equal to 2. So when we think about each of our groups, there's at most going to be 2 values that can be selected randomly from this population with replacement. So the first thing we're going to want to do is we're going to want to fill in this chart with all the possible samples of size n is 2. Keep in mind that you can only choose from these 3 values, 1, 3, and 5. So we only have those 3 particular data sets, 1, 3, and 5. So I'm going to start by saying, let's pick 2 numbers. Now remember, we're allowed to replace these values. So if I went to a bag that had the numbers 1, 3, and 5 written on slips of paper, and I randomly picked the first paper and it showed that it was a 1, I can put that paper back in the bag, shake it up, and pick again. It's possible that I also pick another 1. So there's my first sample. We'll go back to the bag, shake it up, and we'll repeat. So here's my next one. If I pick a slip of paper out of that bag and the first one happens to be a 1, let's say I put that slip of paper back in the bag, I shake it, and I pick again, the next one happens to be a 3. So if we continue with this idea, we're essentially just writing out all the possible combinations for what we could have. If our first slip of paper shows a 1, the second slip of paper can be a 1, a 3, or a 5. If my first slip of paper is a 3, then my next slip could be a 1, a 3, or a 5. Because remember, we are replacing that slip of paper in the bag. So we can pick it again, right? That's why we have these doubles. It is possible to pick that again. Lastly, if my first pick is a 5, then I could also pick a 1, a 3, or a 5. So those are all my samples of size 2, right? They each have 2 values in there. Every last one has 2 values. So the next thing we want to do is we want to actually calculate the mean. Well, that's easy. I know how to find the mean of 2 numbers. I'm going to add them and divide by 2. So if I add them and divide by 2, the mean of my first sample is 1. If I add these and I divide by 2, the mean of my second sample is 2. And I'm going to keep with this process of finding the means for each of my samples until I have them all done. Now, when you do this, it's not necessary to write out the formula every single time. As a matter of fact, after this one, I think I'm going to stop because the pattern is obvious. You add the numbers, you divide by 2 because you're finding the average of those 2 values. So if we go ahead and do the rest of these, we see that the following values represent all of the means. The next thing we're going to do is we're actually going to think about the values that we have, and we're going to construct a probability distribution. Recall, when we construct a probability distribution, we have to think about, well, what are the values we see? Well, when you look at your means, you see that we have a mean of 1, a mean of 2, a mean of 3, a mean of 4, and a mean of 5. So we're going to list those values in our probability distribution table. Let me show you on the next page. The first column is representing the values that we actually see, those calculated means. So I'm going to list them 1, 2, 3, 4, 5. I'm going to go back to the previous table and I'm going to think about how many times I see that mean of 1 appear in my list. Let's flip back. Notice that 1 only appears 1 time. 1 appears 1 time. So when we write the frequency, we say, oh, that appeared once. Let's go back to the mean of 2. The mean of 2 appears once, twice, and that's it. So the mean of 2 only appears twice. Let's flip back and write that the frequency is 2. A mean of 3 appears 1, 2, 3 times. So the frequency is 3. Let's see how many times 4 appears. 4 appears twice. And just for the sake of simplicity, 5 appears once. So 4 appears twice and 5 appears once. Next, we are going to calculate relative frequency. We learned what relative frequency was. That means you basically want to find the probability that that mean is chosen, right? Or that mean is the result. So to find relative frequency, the first thing you do is you say, well, okay, the total frequency here, the total is going to be 1 plus 2 plus 3 plus 2 plus 1, which we know is 9 values. By the way, if you go to the previous page, you'll see that you have 9 different means. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 total outcomes. So that would be the frequency. That makes total sense. Now, the probability that our mean is 1 is going to be the chance of occurrence over the total number of occurrences. So that's going to be 1/9. We could convert this to a decimal, but actually I'm going to leave it in fraction form for now. The chances that we have a mean of 2 are 2 out of 9. The chances that we have a mean of 3 are 3 out of 9. The chances we'll have a mean of 4 is 2 out of 9. And then the chances we'll have a mean of 5 will be 1 out of 9. Next, consider we want to find the mean of the sampling distribution of sample means. So the first thing we're going to do is we're going to take our mean and we're going to multiply it by the likelihood that it happens. Remember, think of that as us wanting to calculate expected value. The formula for expected value is here. So remember this from our previous unit where we talked about probability distributions. That was a formula for expected value. And you know that expected value is the same as finding the mean. Okay, so let's multiply. 1, the outcome, times its probability. 1 times 1/9 is 1/9. 2 times 2/9 is 4/9. 3 times 3/9 is 9/9. 4 times 2/9 is 8/9. And 5 times 1/9 is 5/9. In order to calculate the expected value, aka the mean, we must add up all of the products of the mean times its likelihood of occurring. So we now want to add these up. So I'm going to write here the sum, right? Otherwise, sigma notation. When you add all of those up, that gives you 27/9, which, by the way, 27/9 is 3. Here where we have mean of the sampling distribution of sample means, that's our value here. So the mean of the sampling distributions of sample means is, let's write this correctly, and luckily for us, I have whiteout. I'm like thinking and writing at the same time. So we have 27/9, which is 3. So we found the mean of the sampling distribution of sample means. Super cool. Next, we want to find the mean of the original population. So when we think of the original population, we think to ourselves, well, the population was the set of 3 particular values, 1, 3, and 5. Well, how do you find the mean of that population? Easy. You add the numbers together and you divide by however many values you have. When we do this math, we find that the mean of the original population is actually also 3. That's very, very interesting. What I'd also like to include here is some notation for you. When we think about the mean of sampling distribution of sample means, we're taking that population and we're essentially analyzing the means of all those different samples. So the notation for the mean of the sampling distribution of sample means is going to be mu sub x bar. That is the notation for the mean of the SDSM. The mean of the original population is simply mu, because we know population parameters, we know what that looks like. For a population, the mean is mu. Good. The last thing we have for this particular problem is to note that, well, a couple things. First thing, note that the mean for your sampling distribution of sample means is equivalent to the mean of the original population. That's an interesting feature. We can kind of think about whether or not this is always going to be the case. So we'll talk about that in a bit. But our last step is to construct a probability histogram for the SDSM. So here's how we would do that. Remember that if we're constructing a probability histogram, we know this deals with frequency, but because it's probability, that means that our vertical column is going to be relative frequency, where our horizontal row, or so to speak, our horizontal axis is going to be the actual values that we calculated for our sample means. So the values we found were 1, 2, 3, 4, and 5. So I'm just going to separate these so that it's easier to work with. So these are the sample means that we found. Sample means, and we know that because it's a sample, the notation is going to be X bar. We also know their respective relative frequencies. And because we're constructing a probability histogram, we're looking at these relative frequencies. It goes from 1/9, 2/9 to 3/9, and that's the max. So we can just list those three values on the side. So we've got 1/9, 2/9, and I'm going to make sure they're spread out evenly, and 3/9. And so now we just have to construct the histogram. When we had a mean of 1, we saw that its relative frequency was 1/9. So we're simply going to create our bar here and shade it in. When our mean was 2, we had a relative frequency of 2/9. So notice with histograms, there are no gaps between bars. So we just want to make sure that we don't have any gaps between those bars and they're completely touching. With our mean of 3, that occurred 3/9. So I'm going to go ahead and draw this out. When our mean was 4, that occurred 2/9. The chance of occurrence is 2/9. And then, of course, when our mean is 5, the relative frequency was 1/9. So the chance of occurrence was only 1/9. I want you to notice that the distribution is that of a normal curve. And we learned that from the previous page, that the sampling distribution of sample means is a normal distribution. So this is a normal distribution. Perfect. Perfect. Let's go ahead and turn the page and look at some more information. Behavior of sample means. We will assume that the mean of the sample means, or the expected value of the sample means, is equal to the population mean. So the mean of the sample means is equal to the population mean. That's very important to note here. The distribution of sample means tends to be a normal distribution. This is very, very important to note. As the sample size increases, the distribution of sample means becomes closer to a normal distribution. So we're going to see this in the next section. Next, we have something called the sampling distribution of sample proportions. The sampling distribution of the sample proportion is the distribution of sample proportions with all samples having the same sample size n taken from the same population. So it's the exact same idea, but instead of sampling distribution of sample means, we're talking sample proportions. And we'll learn more about that soon. The notation for proportion is as follows. So P is our population, P hat represents the sample proportion. So it's a notation for a sample proportion. Here's some behaviors that you should know. The mean of sample proportions is the population proportion, okay? The mean of the sample proportions is the population proportion. Next, the distribution of sample proportions tends to approximate a normal distribution. So this is very similar to what we were just looking at. All right. The sample mean and sample proportion, these are statistics, right, because they're samples, are unbiased estimators. They are used to infer or estimate the value of a population parameter. So we use this to kind of inform us about that population. So they are unbiased estimators. Good. Let's turn the page and talk about the central limit theorem. With the central limit theorem, this is kind of an interesting idea about this fact that as sample size increases, a distribution approaches a normal distribution, right? As the samples increase. So I wanted to definitely have this visual for you so that you can kind of see what's happening here. So check this out. For all samples of the same size n, where n is greater than 30, that's actually really important to note. Typically, if n is larger than 30, you'll see more often than not that your distribution will tend to be closer to a normal distribution. So the sample distribution of means can be approximated by a normal distribution with mean mu, that's a population mean, and the standard deviation, sigma, or standard deviation divided by the square root of n, right? That's really, really, really important to know. So the mean is going to be the population mean, and the standard deviation is going to be the population standard deviation divided by the square root of n, where n is the number of values you have in your set. Notice each of the distributions when n is equal to 1, then when n is equal to 10. So first off, when n is equal to 1, that just means that you have one sample, right? You have one set of values. It's one researcher. Maybe they sampled, 30 people exactly, and they recorded those values. So here, you could have started with a normal distribution, or a uniform distribution, or a U-shaped distribution. These are possibilities. Now, let's say that that researcher says, I really want to look at more data. Let me get 9 of my buddies to also do research. So now, when you take 10 researchers that each have 30 people in their samples, notice what's happening to the distributions. Notice that they're getting closer to normality. Let's say that out of the group of 10 researchers, they say this is not enough information, let's contact our buddies, and now let's have 50 researchers. So we have 50 researchers and we each have 30 people in our samples. Now notice the distributions. Do you see now that they tend towards that normal distribution? So as the sample size increase, the distribution of sample means approaches a normal distribution. It's very, very interesting. So let's take a look at the central limit theorem and the sampling distribution of X bar, which is the sample mean. And I'm just going to write that again because I want us to be very confident about that. You are given that the original population has mean mu and standard deviation sigma, right? That's a notation. We're very, very familiar with that. Those are population parameters, values that characterize the population. You would also be given that the simple random samples of the same size n are selected from the population. So these conditions must be provided. So let me show you what happens. Once this information is provided initially, and you know that this is the case, this is like setting the foundation, we can then move to the following two cases. So we have practical rules for real applications involving a sample mean. Case number 1. If we are told that the original population is normally distributed, you're going to use the following information. So for case number 1, if your original population is normally distributed, then for any sample size n, the distribution of the sample mean is a normal distribution with these parameters. The mean of the sample means is going to be the same as the population mean. That's the first thing. The standard deviation of all of those, right? The standard deviation of the sample means is going to be calculated by taking the standard deviation and dividing it by the square root of n. Notice the formula here. Next, if you want to calculate the z-scores for that sample mean, you're going to use the following formula. So I'm going to rewrite this because that might be confusing to you the way that it's written here. So our formula is that the z-score is equal to x bar, the sample mean, minus the population mean, divided by the population standard deviation divided by the square root of n, n being the number of values in your set. Okay? So the population mean of the distribution of sample means is the same as the population mean. And then the standard deviation of the sample means, of the distribution of sample means, is going to be equal to the population standard deviation divided by the square root of n. I feel like writing it out is a little bit clearer, and you can use this as like your key for case 1. So remember, you have to be told that the original population has mean mu and a standard deviation of sigma. And you also have to be told that you're taking simple random samples of the same size from the same population. That's what's allowing us to use this idea of the central limit theorem. Okay. For this particular set of formulas, we know that our population is normally distributed. So what happens in case 2 when your original population is not normally distributed? So let's take a look at this. There are 2 situations here. If n, our sample size, is greater than 30, then the cool thing is the distribution of the sample means is approximately a normal distribution with the exact same parameters. Notice it's exactly the same as before. So we can use the same idea. I'm just going to rewrite what we have to make sure that you all are confident in the fact that we can use the exact same set of formulas. And that's because our n is greater than 30, which lends itself towards that approximate normal distribution. However, if n is less than or equal to 30 or less, the distribution of x bar, the sample means, cannot be approximated well by a normal distribution. And thus, the methods of this section do not apply. So if we were faced with this particular scenario, we would have to use other methods like non-parametric or bootstrapping methods in order to calculate the mean, the standard deviation, and be able to do a z-score conversion. Fortunately for us, or maybe unfortunately, depending on your perspective, we will not be looking at non-parametric or bootstrapping methods. That is not for this class. It is outside of our purview. So the nice thing to note is that in either case, as long as we have information about whether or not the original population is normally distributed, or if it's not, and we know that n is greater than 30, we have the same set of formulas. So we essentially want to make sure that we are using these formulas in either case. I do want to make one other comment. I want you to know, and this is just for your reference, that sigma over the square root of n, that is actually also called the standard error of the mean. That's a very interesting piece to note. Sigma over square root of n, that's also called the standard error of the mean. So as our n increases, it gets bigger and bigger and bigger, the error decreases. If you don't believe me, let me show you a quick example. What if I told you that the standard deviation was 1? Well, if I had, let's say, only 4 people in my sample, then the standard error is 1 over square root of 4, which is the same as 1/2. Now let's see what happens as n, the number of values in our sample, grows. So again, your standard deviation is still 1. Let's say that n this time is 16 people. So we have 1 over the square root of 16, which is the same as 1/4. Notice that the standard error is decreasing. Let's do it one more time. Let's say that our standard deviation, again, is still 1, and that n this time is 36 individuals. So we have 1 over the square root of 36, which is 1 over 6, much smaller than 1/4. So as n increases, the standard error of the mean decreases. As n increases, the standard error of the mean decreases. Good. We're going to go ahead and turn the page and see what the heck is going on. We're going to apply the central limit theorem. All right, let's check it out. Consider a normally distributed population with mu equal to 50 and sigma equal to 15. So notice it's a normally distributed population, which, by the way, is case number 1, right? If you're told that it's a normally distributed population, we're talking about case number 1. And that, again, is from the previous page. Just to show you, here it is. Case 1, the original population is normally distributed. Cool. We're going to use this information here. Suppose a sample of size 9 is selected at random. So immediately I'm going to write n is equal to 9. Note, because we have a normally distributed population, we can use the central limit theorem and our z-score table. So I want to start off by finding the probability that our sample mean lies between 45 and 60. Recall from our previous pages within the same unit, that implies that we are going to find the z-score associated with each of these values. Okay. When our sample mean is equal to 45, we are going to use the z-score formula from the previous page. And that is z is equal to x bar, which is 45, minus the mean. The mean is 50. You know what, if it helps, I'm just going to squeeze that formula up here, just so that you know exactly what I'm using. And again, this is from the previous page. So the sample mean minus the population mean divided by the population standard deviation divided by square root of n, the number of people or number of items in our set. So we have 45 minus mu, which is 50, divided by sigma, which is 15, over the square root of n, where n is 9. We're going to go ahead and do this math. I highly recommend take care of the numerator first. That's going to give you a -5. And then think about this. It's 15 divided by square root of 9. The square root of 9 is 3. 15 divided by 3, that's 5. So we find that our first z-score is -1.00. We're going to do the same thing, except we want to know the z-score when x bar, our sample mean, is 60. Same exact idea. Z is equal to 60 minus 50 over 15 divided by the square root of 9. That's going to give us 10 over 5, which means that our second z-score is 2.00. I'm now going to graph this on our normal curve. We're going to draw this, we're going to label, we're going to shade. And remember, we want to find the probability, the likelihood that our sample mean will be between these two values, 45 and 60. We normalize them by finding their standardized scores, their z-scores. So we go through this process like we did before, and we draw our normal curve, I'm going to try to do this without it looking like crap. Ooh, that wasn't bad at all. Let's label our horizontal axis from -3 to +3. And I try to spread that out and make it all nice and neat. We're going to plot our z-scores. We have a z-score of -1, so I'm going to plot that one, draw a dotted line up to the curve. And then we have a z-score of a +2. So I'm going to plot that as well, draw a dotted line up to the curve, and I'm going to shade the appropriate region. In this case, I'm going to shade inside, between. We want the probability that 45 is less than our sample mean, which is less than 60. So we're definitely finding the area between these two particular z-scores. We're going to go to our z-score table. We're going to look up a z-score of -1.00. -1.00, the area to the left is 0.15866. So the area to the left is 0.15866. The area to the left of a z-score of 2, we go to the positive side. You look at 2.0, that's 0.9772. 0.9772. And then, of course, to find the area between, we know we're going to subtract, just like we did in our previous problem. We did a lot of these, actually. So we're going to go ahead and take our calculator, and we're going to punch in 0.9772 minus 0.15866. That's going to give us an area of 0.81854. What we'll do here is we can now write the statement associated with this area, with this probability, okay? We see here that the probability that 45 is less than our sample means, which is less than 60, is going to be 0.81854. Let's write a statement. The probability that we will randomly choose a sample of 9 whose sample mean is between 45 and 60 would be approximately, remember we're asking for probability, not percentages, would be approximately 0.81854. That is the likelihood that in groups of 9, your sample size, your samples of size 9, the likelihood that the mean will be between 45 and 60 is actually pretty high. If I turn that into a percent, I'm basically saying almost 82% of those samples will have a mean between 45 and 60. That's what this is saying. So we're making an estimation about the population, right? So if we're saying any sample of size 9, the chances it falls in this range, it's almost 82%. Pretty high, pretty darn high. Next, we want to find the probability that the sample mean is less than 60. We want to see how likely that is to happen. Well, luckily for us, when X bar was equal to 60, we found that z-score. We found that it was a z-score of 2.00. Using the diagram from our first part, part I, we see that the area to the left of a z-score of 2 is 0.9772. I could draw the curve again just so that you can feel confident about what's happening here. So if we have our curve and we label it, sorry, this one is definitely not as nice as our last one. And we plot the z-score of 2, draw the dotted line up. The probability that our mean is less than 60 implies that we shade everything to the left. And that's what the table gives us. So when we looked this up, we see that the area to the left is 0.9772. Therefore, we can make the statement. the probability that we will, and notice I'm kind of cookie cutter copying that same statement. It's essentially starting the same, but we're going to say that the probability is less than 60, right? The likelihood that the mean is less than 60. The probability that we will randomly choose a sample of 9 whose sample mean is less than 60 would be approximately 0.9772. So basically we're saying that's really, really, really likely. There's about a 98% chance that that particular sample will have a mean that's less than 60. Excellent. Let's take a look at the next one. We have that the local bakery bakes more than 1,000 one-pound loaves of bread daily. That's amazing. And the weights of these loaves are normally distributed. You are told the population is normally distributed. Guess what? This is case 1. Okay. The mean weight is 500 grams. So mu is equal to 500 grams. And the standard deviation, sigma, is equal to 37 grams. We want to determine the probability that a sample of 36 randomly selected loaves, n is 36, will have a sample mean between 485 and 510 grams. What that implies is we want to find the probability that our sample mean sits between 485 and 510 grams. We're going to do the exact same process as before. We're going to start by saying, all right, well, when X bar is 485, what the heck is its Z-score? So we have Z is equal to, we're going to write 485 minus the population mean, which is 500, divided by the standard deviation over the square root of n. And n in this case is 36. We're going to go through this process. Notice 485 minus 500 is negative 15. And then we have 36 divided by the square root of 36, which is 6. So what I would actually recommend doing here is you can do the following with your calculator. You can say negative 15 divided by, and now I'm going to use parentheses because I want to note that I'm dividing by 37 over 6. So 37 over 6, I'm going to use the division. Notice negative 15 over, and then 37/6 is its own part of the fraction, right? Here's our denominator. I'm going to go ahead and press enter. And we recall that our z-scores must be expressed to the nearest hundredths place, 2 places after the decimal. So our z-score in this case is going to be negative 2.43. Negative 2.43. Let's do the same thing, except this time when X bar is 510. So Z is equal to 510 minus 500 all over 37 divided by the square root of n, which is 36. 510 minus 500, that's going to give us 10 over 37 over 6. We're going to do the same thing. So we've got 10 divided by, let's use parentheses to show that it's 37 over 6. And we get a z-score of 1.62, 2 places after the decimal, 1.62. Very nice. Same exact thing. We're going to go ahead and draw our normal curve. They seem to be getting a little bit worse every time. I'm not sure why. That's okay. No big deal. Nobody's judging me. At least I hope not, right? You better not. We're going to label this. Okay. Negative 2.43. Wow, we're all the way here. Draw our dotted line up. 1.62, we're approximately here. Draw our dotted line up. And let's shade the appropriate region. We know that we are referring to the region between these two z-scores. So here we have our shaded region. I'm then going to use my z-score table. I'm going to look up the z-score of negative 2.43. When I see that z-score of negative 2.43, that directly corresponds to an area to the left of point, and let me just double check, negative 2.43, that's 00755, 00755. The area to the left of a z-score of 1.62, flip to the other side, 1.62, that refers to an area of 0.9474. 0.9474. To find the area between, we know we simply subtract 0.9474 minus 0.00755 is equal to an area between of 0.93985. All right, let's answer this question. The probability that we will randomly select a sample of 36 loaves of bread whose mean weight is between 485 grams and 510 grams is approximately 0.93985. So essentially, what are the chances that the mean weight of that sample will be between those two values, 485 grams in weight and 510 grams in weight? Well, almost 94%. It's almost guaranteed that the mean or the average weight of those loaves of bread of that sample will be between those two values. So very high, very, very high. What is the probability that the sample mean will be greater than 510 grams? Let's write out the probability statement. P, right? The probability that our mean, we want greater than 510, so greater than 510. There's our statement. We know that when X bar is 510 grams, the associated z-score, because we already did this in the previous part, was 1.62. What we're looking for in this case, if we were to draw this out and we draw our curve and we label this, of course, we're going to plot that point and we're going to shade the appropriate region. A z-score of 1.62 is approximately here. Let's draw the dotted line up. And then because we want the probability that our sample mean is greater than 510 grams, we want to shade the region to the right. According to our z-score table, we found the area to the left. That was 0.9474. So I'm going to label this side as 0.9474. If I want the area to the right, we learned that we're going to do 1 minus 0.9474. So let's punch that into our calculators, 1 minus 0.9474, and that gives us an area to the right of 0.0526. So we can say the probability that we will randomly select a sample of 36 loaves of bread whose mean weight is greater than 510 grams, is approximately 0.0526. So the likelihood that the average weight of that sample of 36 loaves of bread is greater than 510 grams is really low. There's only a 5% chance that that's going to happen, right? Because 0.0526 directly corresponds to a 5.26% chance. So it's pretty unlikely. Okay, we have one more question, and that concludes our Unit 6 notes, which, by the way, means that we will be ready for our next test. Da-da-da! Yep, I said it. I said it. Last question. Membership in Mensa, that super smart group, it's basically like a group for like geniuses, requires a score in the top 2% of on a standard intelligence test. The Wechsler IQ test is designed for a mean of 100. Let's write that out. And a standard deviation of 15. Let's write that out. And the scores are normally distributed. Perfect. We're told they are normally distributed. So obviously we're in case 1 again. Find the minimum Wechsler IQ score that satisfies this requirement. So I'm going to go ahead and write that this is case 1 because we're told that the scores are normally distributed. So find the minimum Wechsler IQ score that satisfies this requirement. Now you might be thinking, oh shoot, what was the requirement? Well, you got to score in the top 2%, right? You have to. So if we were to draw the curve, and we've done this before, we've seen this perspective where we were provided with a percentage, but nothing else. We weren't even given like a Z-score or anything like that. The idea here is that in order to be admitted into the group, this region here that I'm shading is 2%. That's the top 2%, which means this is the bottom 98%. Recall that we would write that as an area of 0.98. So we're essentially trying to figure out what is the Z-score that pertains to an area of 0.98. So we are going to go to the positive side of our table, just like we've done with previous problems. And our goal is to find 0.98. So I'm going to start looking across and I'm looking for 0.98. And I see that 0.98 would sit between these two values, 0.9798 and 0.9803. We have to figure out which one it's closest to. Do you see how, if you were to subtract the values, 0.98 minus the first one versus 0.9803 minus 0.98, you'll see that we're actually closer to the left than to the right, which implies that our Z-score is 2.05. 2.05. So I'm going to write here that my Z-score is 2.05. There's my Z. Okay. We are going to note that Z is equal to 2.05. We know that mu is 100. We know that sigma is 15. So we want to find the raw data value. What is that score that satisfies the requirement? That means we don't know X. Notice it's not asking us for the sample mean. We're not even dealing with a sample. Right now, we're just looking at what is the value? What's the score you have to get in order to be admitted into Mensa? Okay, so we're going to use our traditional Z-score formula. Z is equal to, we're going to do this as X minus mu over the standard deviation. We use our traditional formula. So we have 2.05, which is our Z-score, is equal to X minus the mean, which is 100, divided by the standard deviation, which is 15. We're going to go ahead and solve this. We multiply both sides by 15. That's going to give me 30.75 is equal to X minus 100. Add the 100 over, and we get 130.75 is equal to X. Okay. The minimum IQ score would be, now you have to score 130.75 or higher. Keep in mind that your scores are in terms of whole numbers. 130 is not high enough, but 131 is. So it would be 131. So that's the score you'd have to obtain on the test in order to be admitted into Mensa. You don't have decimal values for your IQ scores, it's just whole values, okay? So we would say 131 would be the minimum score. Now, check out part 2. If 4 randomly selected adults, ding, 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 n is equal to 4. If 4 randomly selected adults take the Wechsler test, find the probability that their mean score is at least 119. Interesting. So we want the probability that their mean score is at least 119. At least 119 means 119 or more, right? 119 or greater. So here's your probability statement. As soon as you see here that we're dealing with a mean score, we're finding the probabilities, we're going back to our z-score formula for the central limit theorem. So the z-score formula we will be using in this case is the mean minus the population mean divided by the population standard deviation divided by the square root of n. We're using this formula yet again. Okay, let's plug it in. Z is equal to 119 minus, we know the population mean is 100, divided by the standard deviation of the population, which is 15, over the square root of n, and n in this case is 4. We go ahead and say this is going to be 19 divided by 15 over 2. And when we punch this into the calculator, you'll get a z-score of 2.53. If we take a look at the normal curve, we draw, we shade, all that good stuff. Again, it's always helpful to have a visual. I feel like it definitely completes the picture, right? It's a visual, so of course it would complete the picture. Draw the dotted line up. We want to know, what is the likelihood that the mean score is 119 or greater? So that means we're shading this region here. We are going to go to our z-score table and we're going to look up the z-score 2.53. When we do, we see that it gives us an area to the left of 0.9943. But we want the area to the right. So then that means we're going to do 1 minus 0.9943. That means the area to the right is going to be 0.0057. Okay, let's write a statement. The probability that a random selection of a sample of size 4 will have a mean IQ score of 119 or greater is approximately 0.0057, aka this is highly unlikely. If we turn that into a percent, you're saying 0.57% chance that that'll happen. There's a 0.57% chance that in a randomly selected group of 4 people, that their average IQ score is higher than 119 or greater. Super, super, super unlikely. So I'm just going to write here, highly unlikely. And last problem of unit 6, what if 50 randomly selected adults take the Wechsler IQ test? Find the probability that their mean score, will be at most 129. That means 129 or less. So we'll be at most 129. We're going to go through the same process, right? So when X bar, our mean, is 129, we're going to use the Central Limit Theorem. That formula is for finding the z-score conversion. That's going to be 129 minus the mean, which is 100, divided by 15 over the square root of 50 this time. When you punch in your expression, which by the way, you can do it like this, 129 minus 100, oops, 129 minus 100, that gives us 29. Then we're going to divide this by 15 divided by the square root of 50. Close the parentheses, and we get 13.67. Yeah, I said it. A z-score of 13.67. Okay? Think about that for a moment. If I were to, and I'm just going to turn the page so it's easier to draw. If I want to draw my normal curve, and I'm going to plot, first off, let's label this, right? A z-score of 13.67 is like all the way down here, right? And we want to find the probability that our mean will be smaller than that. So look at what's shaded. Basically the entire curve. What we notice is the following from our chart. Look at the very bottom. For any z-scores larger than 3.49, we will state that the area to the left is 0.9999. Okay? Now we've just reached an example where this comes into play. So let's write our following statement. I'm just going to say that this is going to be 0.9999. We're not going to say 1 total probability because it actually continues on in either direction towards infinity. So we're not going to have total probability being equal to exactly 1. So we can say the following. The probability that a random selection of a sample of size 50 will have a mean IQ score of at most 129 is approximately 0.9999. So basically it's saying that that's almost a definitive statement. That's practically always going to happen. All right, so it's almost definitely going to happen. It's as close to 100% chance as you can get. All right. And on that note, we have completed Unit 6 and we are ready for our next test. I will see you all on Monday. We'll talk about that when we get an opportunity. Make sure you're taking your time with this video. There are a couple interesting topics that might give you a little bit of discomfort at first, but I'm hopeful that with all the examples that we covered, that you feel much better about this and you can tell the difference between when you would use that standard z-score formula versus the z-score conversion for the sample mean. Okay, think about that. I really believe that writing out those probability statements is going to help definitively. All right. Excellent work, of course, and I will see you next class. Bye.